Hello, everybody. My name is Gianfranco Guidati, and I will, as usual, lead you through this lunch lecture. Our speaker today is Jonathan Chambers from the University of Geneva. And your talk today will be on the perspectives on thermal grid modeling under uncertainty. And what I like especially about this title is the term uncertainty, because I think there's something that we are appreciating not enough, really, that everything we say about the future is essentially uncertain. So, Jonathan, I'm very much looking forward. The floor is yours.
Thank you very much, Gianfranco. Go straight into the talk on thermal grid modeling and uncertainty, which is where I will present some of the work that we have been doing here at University of Geneva, as well as some of the outlooks we have for the next stages in the DeCarbch project. So the general background is that we are trying to model the provision of thermal energy services in Switzerland, where we will get our heat from, how do we do so efficiently and in a low carbon way. The top level question, we've been asked a couple of times is, should we decarbonize heat using district heat or heat pumps in individual buildings? And the answer is, of course, that it depends. In investigating what does it mean, it depends, in what circumstances should we use a different technology, we need to understand that determining these technology potentials is subject to uncertainty from a lot of different directions, actually, and I will explore a couple of these directions in the presentation today. We have already, for Switzerland, a few different estimates of the technical potential for thermal networks. This was actually presented in one of the previous lunch talks, and Tobias Sommer actually did a really interesting little review of the different estimates for the future, for the 2050, where we've had something like from between 1.3 times the present day to 3.8 times the present day of potential for heat supplied from district heat networks. And so we want to, it's a really big uncertainty, it's a big range. We want to understand why did this range come up? And so I'm going to start by revisiting a bit of some previous findings, which were actually developed rather in the FEBD project, and think about those again with consideration for uncertainty. So first, we want to think of how do we classically estimate a district heat potential at a country level. So there's been a few methods, but generally it comes down to estimating heat demands per hectare. We have a heat demand density based on some kind of modeling of the energy demand for the buildings. We set some thresholds, for example, in rural or urban areas, maybe we have different thresholds of megawatt hours per hectare. And based on that, we will determine whether or not we have a district heat potential in this hectare. The problem with this approach is that it's a bit of a self-fulfilling prophecy, because where do these hectare density values come from? Well, they usually come from previous studies. A lot of them, when you sort of rewind and you look at who's citing who, and it tends to come back to studies which were done in Sweden and in Denmark, a lot of them dating from more than 10 years ago. And the problem is that if you take these thresholds, you build projects according to these thresholds, and then afterwards you go back and do a review of past projects when you ask, well, what is the right threshold for building a thermal demand density? Well, surprise, surprise, they all seem to follow the same path, because they were all sort of calculated in the same way to begin with. And so, of course, when we want to do future modeling, this is something we need to challenge a bit. So what we did, this was already in 2019, we tried to take more of a multi-criteria approach. We tried to consider a combination of building parameters at the individual building level, as well as aggregate parameters. So, we have building counts per hectare, we have demand per hectare, and also we managed to do some modeling of estimating the amount of pipe that it would take to connect buildings in a given hectare for a given building density. And with that, we could also investigate a bit the interaction between retrofit and district network potential through a few different scenarios. And the idea was that instead of having a single threshold, we could have some combinations of, you need a minimum number of buildings per hectare, you need some heat density, you need some linear demand density, which is, closely related to cost. And so we could get some potentials. We used data on the building stock by pixel. More recently, actually, we released a lot of this data. I think it's quite useful for people, where We have 200-meter pixels, and each pixel actually has a whole stack of data about different building archetypes, which then you can do different kind of data aggregates and so on. And then you can do actual mapping of the spatial distribution of building archetypes, of their heat demands, of their retrofit potentials. So you really try to take advantage of try to understand the heterogeneity of the building stock. So you already take into account this, the spatial variation on top of these different threshold-based estimates, as I mentioned before. And so we got some results. I think we calculated a maximum of 60% of heat supplied by district network, and we did a bit of validation against Levelised. And so, fine, the first look, it seems really good. We reproduce the building selection that was done manually by an expert, by an engineering company that was actually working in the region. I think we even managed to show the difference between the high and low temperature networks, because we included also that in our scenario to say, okay, this area would maybe be better for high or low temperature networks. And so we could reproduce the expert input. But at the same time, maybe that's a problem, because we're not necessarily, we don't know if we've addressed this basic unknown, which is, are we simply reproducing our inputs? Which me as a data scientist is really a common question, and a big issue actually for data science really in general, is that if you build models on the basis of past data, how do you actually predict a future which is different from the past? And if there's one thing we know we want in terms of modeling the energy transition, is we know that we want the future not to be like the past. We want a different kind of technology, we want a different kind of energy system, and so on. And so this led me to think more deeply about how we build these uncertainties. How can we think about these uncertainties in this energy system modeling? How do we think about it when we look at decarbonisation through district heating? We have a lot of key questions, like how much will the demand change? Demands in heating, I think, is particularly tricky problem, because unlike other elements of energy system modeling, where we tend to take demand as a given, we can actually provide heat energy services with very different amounts of final energy, because we have heat pumps, because we have different renewable heat sources. We have spatial aspects, because we know that the demand might change differently in different places. And if we're modeling district heating, of course, this is also really important, because district heating is something which is inherently spatially constrained. And then, of course, we have all these techno-economic parameters which can change. We have efficiency parameters, we have costs, and so on. And so one way to approach this is through global uncertainty analysis. So the point of a global uncertainty analysis is really to systematically explore the parameter space. So as I mentioned in the previous work, what we had done is chosen a couple of scenarios. They were actually scenarios that involved different approaches to demand reduction, as well as looking at the two different kinds of high and low temperature district heating. With the GSA instead, we don't choose scenarios, we just systematically explore all the different combinations of input parameters. It doesn't tell you which one is most likely to happen. So it's not like an ensemble model like you would have in a climate simulation or something. It's really trying to figure out what is the characteristics of the model that you've built. How does it vary as a function of your different input parameters? So it's basically a variation on a Monte Carlo type analysis. As a result, you need a lot of model iteration. So you do need to use computationally efficient methods if you're going to take this approach, which is luckily something that's a bit of a speciality. So this is the paper that we published late last year. That was a geospatial global sensitivity analysis of heat service decarbonisation. So it's a simplified model. We only think about pure electrification of heat services. So we're not trying to integrate too many different technologies, because as I mentioned, we need a lot of model iterations. It becomes very complicated, and already we have a lot of model parameters. So what we're trying to do is think about decarbonising not heat supply, but heat service, which is a little bit different, because we can supply heat services, of course, by having new kinds of heating supplies, so heat pumps, and heat pumps which could be decentralized in individual buildings, or heat pumps also connected to district heating, which we have both in low and high temperatures in the previous work. But also we have building energy retrofit. So we can choose, do we reduce the carbon emissions for heating for a building by saving emissions in that building, or by changing the heat supply? So what we did was adapt this multi-criteria district heating method that was done before into a cost optimization model, where the goal of the cost optimization was actually this provision of heat services rather than just total costs. So what that means is we get the levelized cost of heat equivalent. So we already know levelized cost of heat. It's fairly straightforward. The idea of the levelized cost of heat equivalent is that we try to estimate the cost for providing a certain level of service. And what we do is that we assume that today the amount of energy consumed meets the service demands of people and buildings. So we're assuming everyone today is basically consuming as much energy as they need to provide the heat services that keeps them comfortable, right? And we will instead calculate the cost for a new system, where the cost of the new system will be some combination of electrified heating through heat pumps, centralized heating through district heat networks, or energy retrofits, which will actually just reduce the total demand. So then basically the difference is that we have levelized cost of heat, but instead of dividing by the total heat delivered after we do this energy system transformation, we actually divide by the total energy delivered today, which is basically allows us to include retrofit as a sort of equal opportunities option as an energy solution along with different supply options. And again, it's a pixel-based model. We want to minimize the levelized cost of heat equivalent, again, where the total cost total is the sum of the investment, or the annualized investment for each possible technology, plus the operation and maintenance of that technology and the cost of energy for that technology. So for example, for energy retrofit, we really only have an annualized investment. We have no O&M and energy costs. While for example, a district heating system will be the annualized cost of the heating network itself and the heat supply, which is a centralized heat pump in this case, because we're doing pure electrification. And then of course the O&M for electricity costs for those systems. And we applied this to Geneva and Vaud canton selection. So here I've just showed you the map, because sometimes we have just the illustrative region on Geneva, since it's a bit easier to see. So to apply a GSA, to apply global sensitivity analysis, we used the Sobol sensitivity metric. We used Saltelli parameter sampling. So Saltelli method, it's a method for systematically sampling a parameter space in a method that's shown to be fair. It's basically more efficient than doing sort of a pure grid sampling, because there you would have huge numbers of parameters, of iterations you would need, while it's also more fair than a pure noise-based sampling, randomized sampling, because that would instead not necessarily give you a fair coverage of the problem space. And this was made a lot easier. We've got a package to do this in Python, the SALID package, which was actually developed by a colleague of mine from UCL in London. And then we select a subsection of the model parameters to actually do this sensitivity analysis. You can see this is just the subselection that was used for the analysis. It's already quite a lot of parameters. It's actually 2,500 parameter samples on 100,000 pixels and 259 million optimizer evaluations we needed to do, which because it's, we can optimize quite a lot of this models, it doesn't take that long. It's basically an overnight run of 17 hours. And from this, we get a levelized cost of heat. So these are now indicative results. I say indicative because this is the average across the GSA model runs. What that means is it's not necessarily showing you the average of most likely scenarios. It's just showing you the average when across all of the simulation runs, when the simulation has sort of run in a box around the middle value of the parameters. So we take all of the values of the different key inputs, and then we vary them, sort of, for example, plus minus 20%, or within an acceptable range if it's a physical parameter that has a physical meaning, such as a COP. So these numbers are just to give you a rough idea of like what are the orders of magnitudes that we're getting. And so this is to fully decarbonize the heating supply through this electrification. And we can see, it's a reasonable sort of range. It does go quite high. We're at about 10 cents a kilowatt hour in dense urban areas. It raises quite high when we go to smaller buildings out in the countryside. What's quite important, though, is that when we look at the standard deviation across this, is quite a big variation as well. You know, we're easily at 10%, could be a lot more in some places, and then there's less clear spatial patterns of this. So the uncertainties are actually quite high, and also the distribution, the spatial distribution of the uncertainties is also quite high. We can look at this more detail if we think, well, what is the heat service fraction from each of the options? So what we did is split the results and say what fraction of heat is provided by energy retrofits, what is provided by decentralized heat pumps, and what is provided by thermal networks. And here what we actually show is now the standard deviation of that. So it gives you an idea of the variance across all the different model runs, to give you an idea not of what the absolute value is, but how much it can change. And so this is a standard deviation of a fraction, which you can see basically is 0.5, so 50% of the total. So you have huge uncertainty, actually. When you look around in these areas that are red, this is basically telling you that if the mean fraction was, say, 50%, you could have either 0 or you could have 100%. Would be equally likely for the provision by district heat network. And you see that again for retrofit, for heat pumps. There's a strong correlation actually with the building density. So when you have, it's basically telling you that when you have denser areas, you have more options, and your choice between options is a lot less certain. It's a lot less well defined. When you go out a bit into the more the countryside, where you have less dense areas, you have fewer options, basically because district heating rarely becomes meaningful in some of these. So you sort of only have retrofitted heat pumps. But you know, the takeaway message is, you know, we've got a lot of uncertainty. We don't, if we run this kind of model and we apply a sensitivity analysis, you know, we have a lot of uncertainty in these results, and we can look a bit more in this using the Sobol sensitivity index. So the Sobol sensitivity index is basically related to the first order of differential of the variance of a parameter with respect to its input. You can have second order effects, which is why you can have a number greater than 1. That's not very important. What's really interesting is to see how the breakdown of the total sensitivity index is with respect to the varied parameters. So here we have all the parameters which were used as the parameters which were changed for the sensitivity analysis. So each of these was varied using this parameter sampling technique, the Saltelli parameter sampling. These are the output KPIs, so the key performance indicators, or the key, you know, the key values of the output of the model. So of course we have the levelized cost of heat equivalent, the amount of CO2 savings, you know, the total cost of the technologies, and then, as I mentioned before, the fraction of heat that was provided by retrofit, by heat pumps, by district heating. And this lets you see, out of all the parameters, which is the ones which is contributing the most to the variability. And what you see is, firstly, a really big impact of the cost of retrofit. So this is something we've actually seen before, also in our other work and things that were done by our colleagues here on retrofit, is that retrofits are very expensive in Switzerland. So the provision of heat is very sensitive to how much, for example, you could reduce those costs. So you have a big fraction which is coming from the relative cost of retrofit. You have a big chunk also coming from the efficiency parameters. So the cost of retrofit is basically also strongly related to how much energy you can save through retrofit, because if it's cheaper, of course, you save a lot of energy. So that's kind of an efficiency parameter. You have a big fraction which is related to the energy efficiency of the heat pumps, of individual heat pumps in this case, and a big part which is coming to the seasonal performance factor of heat pumps. And also what is quite interesting, which pops up here, is the amount of power, the maximum power that can be supplied from a low temperature network. So we actually have a parameter which is giving us the peak power, the peak energy, this Q max. If you look here, there's green, which only really appears in the district heating part. This Q max LTDH is basically what is the maximum energy per floor area for a building that can be supplied from district heating of low temperature. So that's quite interesting parameter as well. At the same time, we're still doing something which is based on cost optimization, which is, a bit of a problem. And what I think that a lot of these high variances in these numbers tell you is actually they don't challenge necessarily reality, they challenge our model, because we have huge variance, huge sensitivities observed in the model, very large uncertainties. Does that tell you that reality is necessarily the one that's very uncertain? I'm not so sure, because I think a lot of the uncertainty is basically when we're doing cost optimization and the marginal differences between costs of the different technology options are relatively small. Basically, it's telling us that you can change things one way or the other, and then you can sort of choose whatever you like in a sense. That in the end, probably all of these costs are not going to be the deciding factor in reality. So I think that's kind of what we're finding now, and it's quite an important challenge since a lot of energy system modeling is based on cost optimization. That we're basically saying, well, simply choosing the lowest, the optimal cost option is not telling us that much, because we could change a few things and we could choose another option, and it would also be basically fine in terms of the cost output. So now we need to think what we can do for cooling. Well, for the next directions. Well, okay, we need to think a bit more about cooling. So when we talk about heating and cooling networks, this is important. New technology, a new subject in the sense, because we will have, we have shown also in our research here that cooling demand will increase substantially. We can also try to do a bit more bottom-up modeling with higher level of detail to better understand where we could build district heat networks, and also think a bit more broadly about this part of, how is this decision made? How are we choosing between different technologies? So briefly, I want to show collaboration we did, because I think it's a very nice work that we collaborated with someone at EPFL looking at geothermal regeneration with cooling, where we combined a resource map of shallow geothermal potential, so for borehole heat exchangers, with our estimates of where you could potentially build district heat networks. So we did those colleagues Xiang Li here did a nice spatial allocation method to connect the demands and resources to try and figure out where you could actually use the resource. And this was quite interesting, because then we can see that with this resource exchange, you could get a conversion rate of up to 90%. That is, if you can inject in summer excess heat from cooling systems, you can recover a lot of that in winter again. And it massively increases through seasonal regeneration the potential of using these low temperature district heat networks with shallow geothermal. And one of the reasons I highlight this is because, on top of just being an interesting result, it's something which is not currently reflected in any of the approaches to doing district heat network potential overall. If we're going to choose a district network as an option, at the moment, whether we use the basic heat demand density per hectare I mentioned right at the beginning, or our multi-criteria method, we're still not taking into account what is the added benefit if we can take advantage of these renewable low temperature resources. So that's something that really is something we have to still work on in the future. Another aspect is that we can actually dive even deeper than the hectare, and we can really go to the individual buildings. Now that we have excellent big data sets and we can apply these big data science methods, we've developed some novel methods for accelerating the modeling of district heat network really at the individual building level. So we can do scalable simulation of many possible network configurations. We can do things like sensitivity analysis on this sort of scale. And the idea is that we can further challenge the assumptions through these data-driven approaches by, again, breaking a bit apart these assumptions of saying, yeah, it's going to be this number of buildings, or this district heat demand density per hectare, or so on. And we can look at single buildings in urban areas and say, well, does it make sense? And based on what criteria? And as I said before, we can link that to other types of resources and so on to see to see what the potential could be, what the added value can be of a district heat network when we want to take advantage of a local energy resource. So this is all work in progress, and I think it feeds more broadly into this idea that we need to broaden a bit the outlook. So far, we've looked mainly at this first cloud here, supply-demand balance, the techno-economic aspects. So that's taking general technology parameters, looking at their costs, making sure that energy supply meets demand. So that's one part. Now we've got this optimization. We can start to rethink a bit, what does it mean optimal? Is optimal just about optimizing these costs and this energy balance? Or is it about how we choose between multiple choices and what we mean as the best choice among multiple choices? And then we have another aspect, which is much more about social political. When we build district heat networks, or when we want to choose it as an option, we broaden the number of stakeholders which were normally involved. These are things which kind of need to have both public and policy support, otherwise they just don't work, because you can't start digging up roads outside people's houses without people being reasonably on board with the idea. And so this is also something that we're looking at. We have like an innovation project where we look at this, with the idea that since we're going to bring disruptive changes through this energy transition, we need to think about also how this interacts with public acceptance of big projects. That, you know, beyond looking at this cost optimal approach, we think that probably the technology adoption will follow more the stakeholder engagement, so the different actors of the energy transition and how they will want to prioritize one type of technology or another, irrespective of marginal differences in costs. And so for that, also on the basis, as I mentioned previously, of the scalable simulation of district networks, we're trying to work on this tool we call TESSA, this Thermal Energy System Simulation Assistant, where the idea is that we can do rapid geospatial thermal energy modeling. We can map that with energy supplies and demands, and we can try and start to use this to explore how different stakeholders could engage with the process, how they would interact with this decision to collect data, for example, on what preference might be, which could then feed back into doing more potential modeling at the national scale, by having this more interactive approach where we can also try and extract a bit stakeholder preferences, stakeholder feedback, and see how that affects the design and decision process. So I think I'm just in time now, as I do a quick summary. So we have been looking at the uncertainty in district heat network potential for providing energy service. We've seen that there's big differences in the projections. I presented this work, this global sensitivity analysis, which allows to explore the parameter space of the underlying model that's used for doing the potential calculation. This approach is still limited by the cost optimization approach, and at the moment we don't have an obvious solution to that. But we're starting through sort of parallel works to consider other aspects, for example, the added value when you have things like cooling and regeneration and geothermal, and how might that affect your overall potential or desirability for the given technology. And we've started to look at this bottom-up network modeling view and see how that could maybe unlock more insights into both the potential in terms of physically where we could put district networks, but also how this would then interact with stakeholder feedback on potential plans. And that's the end of my talk. Thank you, and welcome any questions.
Thanks a lot, Jonathan. It was very, very interesting.